Okay, let's take a look at our lesson for today. So far, we have learned 3 of the 10 tests. Just to kind of remind you where we are, we are going to learn 2 more today. We're going to learn the integral test and P-series, so we'll be halfway through all of the tests after today. Before I start on this test, I want to remind you, we really didn't talk very much about sum of a series, so I want to reiterate some of the things that we talked about. Since on your homework there are some problems that require you to do the sum. We talked about sum of geometric. That's that formula, a over 1 minus r. We talked about that. For the sum of a telescoping, actually, when we do the procedure that I showed you last week, it gets it to take the limit as n approaches infinity. It's basically that constant. The other piece goes away. That is the sum of that series. So those two are fairly straightforward to find the sum. If you have another type that you need to find the sum of, unfortunately, what you would have to do is get an equation for the partial sums. You would have to, let's say we took this one for example. This is the nth sum on this one right here. This is the nth sum. And basically the nth term, and this tells us to sum. This is just the nth term. This is the sequence, and this tells us to add everything up. We would have to look for a pattern. I have to put a 1 in here, and I'd get, 1/2. Put a 2 in there. I'd get, 2/5, and so forth. I'd write the terms out, and I'd have to actually write an equation for the partial sums, and then take the limit of that to infinity. So it's usually not something, it's not asked a whole lot to find the sum unless it's geometric or telescoping. But if you are asked to find the sum and it's not one of those two things, that's what you would have to do. You would have to come up with a formula for the partial sums and then take the limit of that to infinity. I just wanted to kind of talk about that before we started the lesson to make sure we're all okay. Alright, so let's talk about the integral test. In order to use the integral test, these 3 things have to be true. Alright, so there are criteria. We can't use it on everything. The first thing is that the function, we're basically giving the nth term. And what we do is we say let f equal, basically we turn the nth term with x's in it, and I'll show you how that looks. It sounds kind of weird, but we basically turn it into a function. We would say let f of x equal the expression. And then we would determine that f is positive, it has to be positive. Second thing is it has to be continuous. And the third thing is it has to be decreasing for x greater than or equal to 1. Now if it's decreasing for x greater than or equal to 2, that's still okay. It has to be mostly decreasing, maybe not for the first couple, but it has to decrease the rest of the time because we're going to infinity, right? A couple of terms isn't going to matter when we're going to infinity. If it is not readily apparent whether it's decreasing or not, what we would have to do is we would have to take the derivative. We'd have to take the derivative, get that equation. Let's remind ourselves, how do we tell if it's decreasing if we have the derivative? We do sign analysis. We'd make sure that the derivative was always negative because that would indicate that the main function is decreasing. So if it's not readily apparent, we would have to take the derivative and just test the derivative to see if it's decreasing. The ones that we're going to do on our notes are pretty straightforward. We'll be able to see if it's decreasing. So that's the first. We have to make sure the criteria fits. Then we set a sub n equal to a function. We set it as a function. And what they say, kind of like they go hand in hand. If the integral converges, then the series converges. If the integral diverges, then the series diverges. That's how the test works. We see what the integral does. If the integral has an answer, like 2, -5, something like that, then it converges. If the integral goes to infinity, then it diverges. So that's how this test is set up. We also we talked about error first in the homework assignment that we turned in. That was the first look at error. Error is Really important topic, and students tend to have a little bit of issues with it, so I'm trying to put it in everywhere that we can. For whatever reason, they like to call the error the remainder. When they say, it's a vocab word, when they say remainder, they're talking about the error. What this formula means is the remainder, using a partial sum of however many terms, is equal to, this is my real value minus my partial sum value, my estimated value. That's the error, or remainder they call it. So I take my real sum, I subtract my partial sum that I calculated, and I get my remainder, or error. What we've done in this one for the integral test is we've bound the error. It's bounded by 0, so here's our error, or remainder, and this integral, n standing for which partial sum we took, the 6th partial sum or the 10th partial sum, and so forth. And we're going to do an example of that. You really will need your calculator for this kind of example. You're not going to need your calculator for the integration, but you are going to need it for the remainder portions. All right. So let's take a look at our two problems, our two integral. We're going to determine whether they converge or diverge, and we're going to practice the integral test. Certainly there may be other tests that we could try on these, but what we're working on is the integral test. So let's do that. So the first thing we do, we say let f of x equal x over x squared plus 1. That sets up my function. Once I do that, I have to determine if these three things are happening. The first thing, positive. If I put this number 1 or any other number, 2, 3, 4, 5, into this expression, am I going to get a positive number? Yes. So it's positive. We can check that off. We would say f is positive. All right, continuous. If I used numbers from 1 to infinity in here, would I get a continuous function? Yes, it's continuous. The last check is decreasing. If it's not going to be readily apparent to be decreasing, we'd have to do the derivative. So let's check. Let's see, if I put a 1 in there, I get 1/2. If I put a 2 in there, I get 2/5. 2/5 is less than 1/2, right? If I continue putting numbers, it generates smaller and smaller numbers, so it is decreasing. So this one we can tell by inspection. What that means is you don't have to prove, you don't have to offer a proof of these things on the AP test. You simply have to basically look at it, inspect it, and say that they are true. They will accept that. That'll be fine. You don't have to say it's positive because I tried all these numbers in it and they're positive. You don't have to say that. You can just state these three criteria by inspection. All right, so we have the setup. We are able to use it. So what we do is we're going to write it as this integral. So we have the integral from 1 to infinity of x over x squared plus 1 dx. That's an improper integral, so we would rewrite it using the technique that we learned a couple units ago. So that's the limit as b goes to infinity, integral 1 to b of x over x squared plus 1 dx. That's the limit that we're going to be working with. So hopefully we recognize that that's a u sub, where I would set x squared plus 1 equal to u. Now for some of us we can do that in our head, and I encourage you to do that. I'm going to go ahead and write it up here. U would be x squared plus 1, du would be 2x dx, and I'd have to move the 2 over, so 1/2 du equals x dx. Now those of you that are doing this in your head, remember the 1/2. Don't forget the constant. All right, so what we are left with is basically this is going to turn into 1 over u, or 1/2 1 over u du. So we have the limit as b goes to infinity. So that gives us the integral of 1/2 natural log x squared plus 1. I just did the integral. I didn't write it down. I just worked. That's the integral, or the antiderivative of this, from 1 to b. All right, so let's sub in. Limit b goes to infinity I have 1/2 natural log of b squared plus 1 minus 1/2 natural log of 2. All right, what happens to this term right here as b gets bigger and bigger, as it tends to infinity, as it goes to infinity? What's going to happen to this first piece? It's going to go to infinity, right? Natural log of 10, natural log of 20, natural log of 50, natural log of 100. It's going to get bigger and bigger numbers. So this diverges. That limit would be infinity. And so by the integral test, if the integral diverges, then the series diverges. They go hand in hand. Whatever the integral does, that's what the series does. So we would say, therefore, diverges by the integral test. Okay? All right, let's look at our next example. So we started out the same way. Let f of x equal 1 over x squared plus 1. So we look at it and we say, okay, is this going to be positive for all of these terms from 1 to infinity? Yes, it's positive. Is it going to be continuous from 1 to infinity? Yes, it's continuous. Is it decreasing? We can probably do this one by inspection also and not have to do the derivative. If I put a 1 in, I get 1/2. If I put a 2 in, I get, what, 1/5. The numbers are getting smaller, so it's decreasing. So it is decreasing. So we are eligible to do the integral test. Okay. So let's do that. Let's set it up. So we have an integral from 1 to infinity of 1 over x squared plus 1 dx. And it's improper, so we set up our definition. So the limit as b goes to infinity, integral 1 to b of 1 over x squared plus 1. Now hopefully we immediately recognize that that's arctangent. Right, 1 over x squared plus 1, arctangent. So this is going to be the limit as b goes to infinity of arctangent from 1 to b. All right, the limit as b goes to infinity. So let's do our f of b minus f of a. So it's going to be arctangent b minus arctangent 1. Now, if you don't remember what the graph of arctangent looks like, you may be misled here. The graph of arctangent has two horizontal asymptotes. Remember that? It has a horizontal asymptote at pi over 2, has a horizontal asymptote at negative pi over 2. Hopefully we remember that. I'll sketch it up here. So it's got horizontal asymptote at pi over 2 and negative pi over 2. And it goes like that. So as we head to infinity, what is that going to tend to? Pi over 2. So this is going to be pi over 2 minus arctangent of 1. Well, whatever that number is, that's a number, right? The limit or the integral is going to be an actual number. So since the integral equals a number or converges, then the series will converge. So therefore, converges by the integral test. And those are two examples of the integral test. Okay, we okay with that? All right. Let's take a look at the remainder. This formula right here, I am not going to require you to memorize that formula. If I want you to do the remainder, which I will give you the formula. Okay, that's not one that we need to memorize. So let's see what it says. Basically that our error is bounded by 0 and this integral. What this example is asking us to do is first approximate the sum of the convergent series by using 6 terms. Okay, include an estimate of the maximum error for your approximation. All right, so approximating, we would need our calculator here. If you have the new operating system, it's pretty easy. You just do, I think it's math 0 on the new operating system. It's a summation on that menu. If you don't have the new operating system, you're going to have to get to it a little bit of a different way and put it in differently. Like if you have an 83 or an 84 that does not have the new operating system, you're going to have to use this format over here. I'm going to write it up here for those students that are looking at the video notes. It's sum, sequence. We would write our formula, our nth term formula here, the nth term formula, comma x, comma our starting number in the that we're going to add. So in this case it will be 1 to 6. The way that you get to these commands, the sum and the sequence, are it's like in the list, second stat, and one of them is in the math pull down menu and one of them is in the ops. So it's a little bit more cumbersome to get to if you don't have the new operating system, but you still can get to it. And you would have to type it in this sequence. Okay, so it's under second stat. It's in the list. One of them is under math and one of them is under ops. So at any rate, you can do that, or that's probably the fastest way to do it, is to use the calculator to calculate the 6 sum. What we really are doing, which you practiced on your homework, is we really are writing out the first 6 terms and adding them together. I'm going to do that. This would be S of 6. You do not have to write out the terms unless it asks you to. You could just go straight to the decimal. But I'm going to go ahead and write them out. And then over 1296. So this is approximately, in decimal form, 1.0811. So that's my that's my partial sum of 6. I use 6 terms, S sub 6. So let's look and see what an estimate of our error would be. So using this formula, our error is going to be between 0. Now I'm going to find the error at 6, or the remainder. They like to use the word remainder instead of error. And that's going to be between that and this integral. Integral from 6 to infinity of f of x, which is 1 over x to the 4th dx. Okay, so let's do this integral right here and see what that is. Alright, so it's an improper integral. So the limit as b goes to infinity, integral 6 to b of 1 over x to the 4th dx. So that's just the reversal power rule. It's negative 1/3 x to the negative third, or limit b goes to infinity, negative 1 over 3 x cubed. Let's write it like this. Evaluated from 6 to b. So I do my f of b minus f of a. So I put the b in, I get negative 1 over 3b cubed minus a minus, so plus 1 over 3 times 6 cubed. So what does this first term tend to? It tends to 0. And I'm left with this, which is 1 over 648. So that is the biggest error that I could have in my estimation is fairly small, isn't it? 1 over 648. Now, I will tell you the way that they like for you to write it. So I think this makes sense that the error is between 0 and 1 over 648. I think that makes sense. Actually, what they like for you to do to finish this up is to add the 1 over 648 to your estimate to find the maximum value for that. That's what they want you to finish up with. So you can write it like this, showing the error. Now let's use the error. If we had the maximum error, what would this sum equal? So I would do this 1.0811 plus, and of course I would have a calculator, and I'd get some kind of a decimal. Oh, I didn't write it down here, but there'd be some decimal answer, and that would be your final answer. That would be your maximum error. That's the biggest the sum could be. Okay. Alright, does anybody need some more time to write? I need to go to the second slide. Are we okay? Okay. Let's look at our next test. The next test is P-series. This is a specific kind of series. And let's take a look at what they look like. So 1 over into some power. P is the power. So P series. For P equals 1, this series right here, it actually has a name. It's called the Harmonic Series. And sometimes they will just call it by its name. This is like a vocab word. You need to know what this vocab word means. They may not even write the series for you. They may just say, use the harmonic series to blah, blah, blah. I mean, you need to know when they say harmonic series, they're talking about the P series with a P of 1. Okay, so this is a vocab word you need to know. And so there are rules for the P series. We could use the integral test to calculate what values of P would cause this to converge or diverge. And I'll just work one of them for you. And I'm hoping that you will see, certainly if you forget which is which, maybe you could do the integral test real quick and see what happens. So we'll go from n equals 1 to infinity of 1 over n. Let's do the harmonic series. This is positive, continuous, and decreasing. So we are allowed to use the integral test. And the integral test tells us to do the limit from 1 to infinity of 1 over x dx. And so we set it up, limit as b goes to infinity, 1 to b, 1 over x dx is the limit. B goes to infinity, so the integral of 1 over x is ln x, evaluated from 1 to b. So we have the limit as b goes to infinity of ln b minus ln 1. So what's going to happen to this term as we head towards infinity? It is 2, isn't it? It's going to tend to infinity. It's going to diverge. And by the integral test, if the integral diverges, then so does the series. The series diverges. So this diverges. So up here, they actually have this as the last part C. So the P series diverges if P is 1, which is, the harmonic series. Now, just to save some time, I'm hoping you can see how that procedure works. Just to save some time, I'm not going to do the integral test for these two, but you could to kind of develop the pattern. We're just going to kind of cut to where the other places that it diverges here at 2. If you do the integral test, you will see that the integral converges. So what that tells us is that when P is greater than 1, the P series converges. This one at 1/2, if you do the integral test, you will see that the integral diverges. So that tells us that when P is less than 1, it diverges. So let me finish writing these up here for you. The P series converges if P is greater than 1. The P series diverges if P is less than 1 or equal to 1. So this needs to be committed to memory. Now, unfortunately, sometimes students get them backwards because it's kind of counterintuitive. If P is really big, it converges. That seems kind of weird, doesn't it? If P is bigger than 1, it converges, but if p is smaller than 1, it diverges. So that's something you just need to kind of set in your memory. It's going to be pretty important. And when you see one of these that needs the p-series, you're going to go, oh, how awesome, we get to do the p-series. Just like with geometric, oh, how awesome, we get to do geometric. Probably some of you already see what p is without even having to rewrite it. I'm going to go ahead and rewrite it so that it's very obvious. You do not have to do this. You don't have to rewrite it if you already see. So this is into the 1, into the half. Common bases we add. This is into the 3/2. So p equals 3/2, which is larger than 1. Therefore, what? It's larger than 1, so it will converge. Therefore, converges by p-series. See how nice and easy that is? Okay, so that's our p-series test. And now we are halfway done with our tests. Wow. All right.